Okay, this is the assembly file, which is today we're going to be lesson number 3, analyze the assembly problem with some contact. So when you have a mechanical part, which is more than one, and it's assembled together, you have to assign the contact conditions, and that's quite important to your analysis. So lesson number 3 that we will learn, we will do the pilot, which is we have 3 components for the pilot. And then now we have got the model, which is explode. So if we go to the configurations, and then we click on the default, you see the Explorer views. If you click right and then say collapse, that will assembly together. And if you would like to see the explode view again, just click right on the same place and say explode. Okay. And also in the explode view, if you extract, you will see explode step 1, which is the part of arm. You can move and just rearrange the positions as you want. Okay. Explode step number 2, which is the pin. You can move like this. Okay. So just an explode view. Okay, and then we go back to the model 3 of the pliers. And then as you can see the parts, we have 2 arms, we have 1 pin, and actually we have a flat. Let's unspace on that flat. Unspace to show the feature. This one. But I don't need an explode view. Okay, but like this. Okay, so the problem is, so we have a tool, which is a plier, and then it's just contact with some flat plate. And on that, when we analyze, we will just get rid of the plate, and we will give the restraint instead of the plate. To let them say, at that part, at the jaw, they will have something contact and squeeze something, which is a flat plate. Okay, so that's why flat ones, we have to suppress into out of the model because we're not taking into our calculation. Okay, so suppress it. And then in this tool, on that surface, we have to apply the conditions, which is a restraint that to say that it's fixed because it's replaced with the flat. We will set that fixed. Also, the outer surface. here as well. That should be fixed. Okay. And then on the end of the arm, we will apply some load, like the way we have when we operate it, we use the hand to squeeze it. Just give compression. And the compression we put both sides as well, upper and lower. And the load we put on, that will be 225 Newton. Okay. For the material of this, so we use, what we use? Plain carbon steel. Plain carbon steel. Okay, so after we suppress the flat, we go to create a new static. The name is static 1 and analyze with static analysis. That will be fine. Okay. On this, for the part, if you extract the model 3, you will see 2 pieces, 2 arms, and 1 pin only. No flat. The flat will not take into your consideration. Okay? So if you go back to the model, if you not suppress this part, when you create a static analysis, the part will came to your consideration. Okay, just suppress it before. Okay, 3 parts here, 3 parts here, and we will apply all the materials, which is plain carbon steel. We keep right on parts and apply material to all. My computer stuck. Can't take anything. Okay. Circle. What's wrong with my computer? Okay, they came, but really slow. Okay, plain carbon steel, apply and close. And you see on the model 3, you have the material in the blanket of each part. Okay, that's first step. Apply material. And then we're going to create a fixed geometry. So on the features, we say fixed geometry. And on the area of the jaw, lower and upper. Fixed geometry, 2 surfaces. And then click OK. What's wrong on my computer again? I can't click. Let's do that. Okay, that's fixed geometry. That's replace the flat. And in the conditions when we operate, actually, so it's like the plate and the jaw is just fixed to each other, not move and no slide. That's why we say that's a fixed geometry on that surface. Okay, and then we apply force. That's just the normal position. Upper and lower, squeeze. And the size, 225 Newton. under the load conditions, they have say reverse directions. Let's check on your screen that show the arrows, the directions correctly or not. And under that, they say per item. Per item here is mean on each surface that we applied force 225. And if you say total, that means both of them together, the total load is 225. Okay, that's separate. And then that means it's a half, right? Half up and half down. So we need just per item. And the force applied on normal, we didn't use the selected directions like the last time we have done, okay, because that is show normal to surface force applied. Okay, that's it. Okay, and then that's for just a normal procedure, and then if we do the normal procedure, we will create a mesh. But before we're going to do that, we have another condition here, which is the connection. When you have an assembly, you have to provide these conditions every time when you have an assembly part to analyze in your geometry. Okay, for the connections, if you take an arrow down there, you will see the component contacts. Component contact. That means the overall of the part of the assembly that we have a contact, and you can set it there. And the default of the program is already say it bonded. What does this mean bonded? So if you go here on the PowerPoint, so we have three types of contact. One is bonded, which is default of the software. And that you can see part A and part B, which is different material, different part. But when you take into the simulations, the node at the contact surface, that will be the same. It's like it's bonded together to be the same part. When it moves, it will move together. Okay, the advantage of this, when we create a contact and bonded, it looks like a same part because the material will be touched all the way when you move. The advantage of using this is that you can apply different material in one part. Okay? The modeling is the same as one part, but the advantage is you can apply different material in one part. Okay, and another contact, which is a free contact. And in the program now, a new versions, we use allow penetration. Okay, allow penetrations of free contact. That means two material just allow to override to each other. That's the figure saying. And the last one, the last conditions is a contact, which is no penetration. Not allow another material go inside another material. Okay, so that's an option for your analyzing. Okay, and then let's go back to SolidWorks. So here, if you click right and edit definition, you will see the default, which is bonded. Okay, and it says the components is global contact. Global contact means every contact is set bonded. Global is mean overall of your assembly. Okay, so I just click no first, and then before we go to assign the contact conditions, I will go to evaluate menu. Evaluate menu on that. Okay, and then I click on the interference detection. I would like the program to detect the surface which is have a contact first for me. Okay, and the program reads all the parts in the assembly, which is we have three parts. And then we just go down there and click treat coincidence as interface. So when they catch up the coincident conditions, they will just say, oh, this is interference as well. Okay, and then go up and say calculate. Okay. Go up and say calculate. The program detected three interferences. Is that okay? Any problem? Okay, three interference. If you click your mouse on interference number 1, that will say the lower arm interference surface with the pin. This is the coincident conditions between surface of the arm, which is a whole surface, and the surface of the pin, which is the surface outside the pin, contact. That interference number 1. Interference number 2 is just between two arms. Two arms that have the red area there, that's the contact surface. Okay. And interference number 3, that is another arm, the gray one, contact with the pin. That 3 interferences. Okay. That's it. We click OK. And then we go to the global contact again. Now we know each contact we have, and it's not actually bonded, right? Each part has to move. Each part has to move, and each part didn't allow to have a penetration. So in these conditions, we choose no penetration. And on the components down there, they say global contacts. That means for all, for 3 interferences, for all of that assembly. Okay, and then okay. We have the global contact, which is no penetration. Okay, and then last time I forgot to teach you to check the options of simulations. So if you go to the main menu on the top and go for the simulations, just pin them there. Okay, simulations, and go down for the options. Simulations option. Okay, we will have the dialog box. I go to the default option. Okay, the first one is the options about the unit. Unit we use SI, and the length, temperature, velocity, pressure, and stress. So for pressure and stress, I would like to choose megapascal. Okay, and then below the feature, show colors and no shades. For the mesh, the mesh quality default is high mesh quality. image quality. Okay, and then in this box down there, show advanced options for contact set, definitions, no penetrations, and trim fit only. So we need to tick that options because our conditions is no penetration. Okay. You have to check when you do some analysis. Okay, and the rest of that is just some result. So we use just default of that. So, and this one we just show you the number of the result. Now we choose the formats of scientific with 3 decimal. Okay, that's fine. How can I just go down to click OK? It's down there. What should I do? I can't minimize. Let's say enter. Is that fine? You see what the scale of the monitor changes? Can't see it. Okay. Because it doesn't change to anything else, right? Check again. Okay, megapascal. Okay, enter. That's fine. Okay, and then so we have to create image. Go to image and create image. Image parameter. We use the curvature base. And then just change the maximum and minimum element size to be 4.912 and 0.982. For the number of elements in the circle, it's just 8. The ratio is 1.6. And for the advanced, so we try to use a DAF quality image. Otherwise, that will take a long time. So just use graph quality image. And then OK. You will see the image. And if it's not clear enough, so go back to the configurations and say explode. Okay. And then go to the simulation menu and run this study. That's it. So I will choose the result, show me floating format. Change here. Okay. Okay, you got it? Okay, let's interpret the data we got. So for the analysis, we got the volume stress, which is shown in the megapascal. And now we have the maximum, is about 98 megapascal. For the yield strength, show us that the pen common seal have a yield strength at about 220 megapascal. So that means our tool is not damaged or not anything happened because it's quite lower than yield strength, right? And then in your design, you may need to change the scale of the label here. So if you think that is your yield strength is about 220, and on the scale you will say your design, the stretch shouldn't be over than 130. So let's just try to change the maximum and minimum of the scale from 0 to 130. That's about 60% of the yield strength. So we can just double click on the level scale color there, and that will show the charge options. We change the automatically define maximum value and the minimum value to be 130 and 0. That's it. And that means the result we show you, if any point have a red color, that will be over your design. Okay, but we already done that to know the maximum of this already is about 98. So that means nothing over than 130 megapascal. So that's just try to change the scale to make it easy to read and easy to understand and just relate it to your design and your condition. Okay. And then what else? Let me check. Okay. For the result, we can go to, you click right and go to define stress plot. So actually you can just say the chart option here and set the value that you would like to display and the unit of that parameter. And if you go to the advanced options, to show just only one part. So for example, I just need to show a plot only on the selected part, selected entity. And then click on the body options. And then I click on one arm. and show the nodal values. Okay, and now that, so for the deformed shape, we can use a scale for the deformed shape of your assembly. So now I use true scale that like exactly the same size, the same deformations that okay on your assembly. So just true scale. And actually you can define if you want more to show that more deformed, but the number doesn't change, just change the shape on your program only. Okay, it just says that true scale. Okay. And that will show you only one part. And then if you would like to change the maximum value and minimum value again, yeah, just do the same. Yeah, that's it. That will be no red color because the maximum value is 98. If you like to show floating format, so just change from scientific to floating. That's it. Okay. And then on this one, have you noticed that we didn't try to do remission for more accuracy because that is just for your option. So this is just show you how to analyze some of the assembly analysis with some contact. But anyway, for the result that you get from simulations, the revision of the model that required. Okay, you cannot say that is the correct answer yet. So you have to make sure the answer by doing the rematching and see the converge of the result before the answer. Okay, and then if we go back to the stress and then the collapse, the model. That will look like this. For the displacement, yeah, we didn't see the displacement. You see the displacement here? That will show you the moving part quite a lot. A large deformation is over there at the end of the arm. It's about, let's show floating format. It's about 0.4 millimeters, not too much. So sometimes the program will show the scale automatically. For the form shape, you have to check if you choose the automatic scale, your result will show like this. Don't trust them yet, because that is just default shape scale, which is too high. And you can see on this box as well, to say the deformation scale 54. That means for actual deformations, they will times to the 54 to show the deformations over that is B. But that's just scale of the feature, not the number of the deformation. The deformations number, not the same, not changed, just the feature, just on the picture to show you the scale. So when you got something like this, you have to check the scale that we use and the definitions change to true scale, that would be an actual deformation, actual shape, and actual size. And then in this one, it shows you the resultant of stress. But if I would like to show only y directions, so define displacement plot, and you can choose this to be only uy or y displacement in millimeters, true scale. Yeah. The result will create another displacement, which is only y directions to show you. And as you can see on the scale here, the maximum deformations, maximum displacement is about 4.1. That is positive directions, and another is a negative directions, is about 4.1 as well. Okay, that means the moving part, the blue one and the red one, is moving together. Okay, and the distance here, if you go to the evaluate and use measure and just choose a point to another point. Right, so no. The distance between that arms is about 15. And when we squeeze with the load, 225 newtons is moved just only about 0.4 each to move close to each other. That is about 0.8. Let's say that part will move close to each other, and the moving displacement is about 0.8. Okay, because one is moved down and another is moved up. So that is makes closer. Okay, and that let's try to do another analysis, which is if two parts contact each other. So that means if it puts the load more than 225, so next time we will put about 4,500 meters. And we would like, we just expect two arms contact each other. Okay, by put some more load. Okay, that's this one, just close. Okay, let's step. So what's wrong on this? Mesh not current, the results have been changed. Okay, because we changed the result. Okay, that's one. Okay, next one, we topic study. And let's say static 2. The configurations only have one. We have only one configurations, which is default. And the target study, which is static analysis. That's okay. In this study, let's change the force, in the definitions for the force, to be 4,500 on per item and normal to the surface. Okay, change the load. And then So be careful when you have more load on the assembly, and that we just guess 2 arms will go contact. And for the contact, on the level of connections options in the module 3, so when we say the component contact, that means on the top level down there, the red color there, which is like a global contact that we have to set, that we have to for the assembly. Okay, and then when you have another contact, which is in our assembly, we have 3 interferences that we already done for all, which is a global. But sometimes you may have a individual contact of each couple. So we need to put some other component contact. And the last one, which is really important, it is a local contact. So that the things that we have to set when we have something serious or something that is concerning on the contact. Okay, so that global contact to the local contact. Let's go back here. To the connections options, the global contact is already set. And then we will do a local contact. For the component contact, I think 3 interferences just the same, not changed, so that I don't have the connections contact. So I will just create a local contact by say contact set. Contact set. Okay. For the contact set, we just guess that 2 arms will move close to each other. So I will choose this surface, and another surface, choose the lower one. Okay. Because we think when we squeeze with the load 4,500 Newton, so that will make 2 surfaces come to contact each other. And we just create the local contact over there by 2 surfaces. And then for the options, for the type of contact, the software have no penetrations. We have bonded, which is no bonded, and allow penetrations, which is that's quite obvious because our material cannot go inside each other. Shinfrit, that used for when you have like some things put in order, like if you put some pin to make it fit with the part, that will be shinfrit. And the virtual wall, that will be just a wall, conditions that contact the wall. In this, so we will choose the no penetrations. Right. Contact set, no penetrations again. Okay. Okay, that will be our local contact. And that's okay. So let me now 3 interferences around here, around the rotating part, around the pin. That will be 3 interferences, is no penetrations, and another local contact at the end by the force we apply. We just say no penetrations as well. Okay. The difference between the global contact that we set and the local contact that we set. The difference is if your assembly have already contact each other, you have to set as a global contact all the component contact because it's already touching. But for the other, which is a local contact, that will be happen after it's subjected to the load. It might be happen or it might not be happen. So we set at local condition. And then in this one, go to the simulation option again. Check that we have show advanced options for the contact set or not. Okay, we already ticked that. Okay, and another one, let's check back to the local contact again. I didn't show you the advanced. So this is local contact. So for the advanced options, we have an options about node to surface or surface to surface. So that really means on that two surface over there that we pick up upper arm and lower arm surface. When we compress and it can go move close to each other, and the F1 say it will be stop, not go penetrations. It will be stopped because it's no penetration when some nodes on each part contact the surface of the other part. Okay, that's an S1 option that we should. Okay. And for more accuracy, we go to the static to study, click right, and go for property. There. Go for property. Okay, in the static options, we will tick on the improve accuracy for no penetrations contacting surface. Just provide you some improvement of accuracy. But it will take longer time to calculate. Okay, just tick that. And then just show you some options. So in SolidWorks, we have an adaptive method. We haven't used that before. The default is show none. So for adaptive method, that we have two options, which is H adaptive and P adaptive. So for H adaptive, the options will just rematching for you. Depends on the result of the previous result. And the program will run another by rematching itself. Okay? And for P adaptive, it will just concern about the order of the elements. So remember on CAE number 1, we have triangle elements, which is 3 nodes. And we also have triangle element with 6 nodes. That's different order. That we get more accuracy. That P adaptive and H adaptive will help you with that result, but we don't use that yet. Okay, just improve the accuracy of the contact, no penetrations, and then click OK. And then check on mesh. Create mesh. Mesh parameter, curvature again, and the size is already there. Okay. Okay. And after you create image, and then just run. And this just a warning to show you have a specified node to surface formulations. Okay. And then, yes, just continue solving. And then we have just some message again that we just found the excessive displacement. It's like now we have a large displacement, and they just ask us that you going to calculate or not, or calculate without the large deformation. So this one is like, do I have a graph here? No. Let's go. I think I just have some graphs there. Okay, like this. Or let's say raise the dialog. Let's say no first. Raise the dialog, raise one. Yeah, let's say no. Let's say run without loss informations, and I will give you explanation here. So establish is not okay. So for our analyzing is on static analysis, and on the engineering design, we try to use the property of the material on the elasticity. Remember elasticity, a linear deformations, and that means when your assembly have deformed and have the large deformations, that means it really out of the elasticity. Okay, and the program just asks that you trying to do large deformations or not. That's the property will be changed to be other property, not in elasticity. But if you're concerned about only just on elasticity, so we just say no. Just take it then like have a constant Young modulus on that region. Okay, so that's why the programs arc. Okay, and then we say no, and the result runs faster. If you say yes, it will take longer time because they were concerned about the property on outer regions, like go out of the elasticity, go for plastic deformation, glass deformation. Okay, and then yeah, you can show the wall stress. You can see the displacement and the up to you the options how to show. And as you see, let me show you. Some of the computer might have set the automatic scale, and that will go like this. Go like this. If you choose the automatic scale, but you have to change the scale to be just true scale. And then be like this. And that's the actual informations, true scale. And you see at the end of the arms, so we have set the local contact. So by put 4,500 newtons, that will make the arm stick to each other on that contact and no penetration. For the displacement, that shows you the true scale deformations. Okay, and the strength strength. And you can explode view to see each part. That up to you. Let's go to the warm mist again. On this one, let's show in the floating format. On this one, you see the maximum. Let's show maximum as well. Maximum. The maximum stress is about almost 2,000 megapascal. Yield strength is only just 220. That means your plier is going to damage, is going to be broken out. Okay, I think that's it. Okay, and then we have some to do some of the quiz. This one, let's and then I close it. Okay, in the e-learning, I have put some auto assembly, which is 2 rings. You have downloaded already, and then just open that file, 2 ring assembly. Okay, that's the process. So on 2 ring assembly, we need to put some force. The figure is too small. Oh, I think I have it on PowerPoint. Okay. 2 ring assembly. So in this problem, I want you to give a fixed restraint on that part. This on the bigger ring, which is have a surface square here, and then have a partial restraint on that, and have a pressure load on another surface. And the result, I would say something like this. Okay, but I will guide you first for the material and the some of the conditions. Okay, you open that. Open assembly. Check the simulations option, the default options on unit. Yeah, use megapascal, load, image, and resolve, and the color chart. So let's say maybe floating, we use fiber. Okay, set unit and set and check image on the contact set definitions and go for color chart. Show the number formats as floating and 3 decimal. Okay. And then this one we don't have to space any parts because we have only two parts work together, no subtractions. And then we go for new study, static number 1 and static analysis. Yes. For material, we use AISI 1020. AISI 1020. Apply and close. Check on parts. We have AISI in the blanket. And then we do the fixed geometry. And fixed geometry should be on that square surface. Fixed geometry. Okay. And another conditions, I will just you to click right on feature and go for advanced feature. Go for advanced feature. Okay. For the advanced feature, we use reference geometry. This box. And then I will choose full surface. Allow this base. Full surface. Okay, use reference geometry. Choose full surface. And on the pink box there, I will just take the fly out, choose plane number 2. Choose plane number 2. And then go down, translations. I pick the directions of along the plane direction 2 and normal to plane direction 2. This. What does this one mean? This is not fixed geometry. It's a use reference geometry. It means that we try to fix only 2 directions. Just leave one direction free. I choose full surface over there, around that, which is to fix that surface on the X directions and Y directions and Z direction. And just refer to that coordinates X, Y, and Z there. So I mean, in this part, when we actually apply load, actually we apply on this on the real life, but in simulations we just change that to be fixed and just try to put some load on the other side instead. And to confirm that fixed part over there, that's a fixed part, it's not moved in Y and Z directions, it's just moved on this directions only, in X direction. So that we use the reference geometry to be the conditions of the free string. Okay? And then click OK. And then external load. Now we choose pressure. And the pressure we use is in megapascal. Make sure you check the unit. Megapascal. And we have 3.5 megapascal. Oh, forgot to choose the surface. Choose this surface. And reverse directions. Okay. Okay. Click OK. Okay. And then let's check the component contact. Default is bonded, but for us, it's not bonded. Two rings is not bond to be a one part, it's separate part, but it just have a contact. And the contact that we set, that would be no penetration again. No contact, no penetration. Okay. And this one, we use mesh control. The other one, the last one we have done, the first one, is just global mesh, right? Global mesh. And have set a ratio that they will try to create mesh in the part, in the area concerning with stress concentrations, not use a mesh control. But on this one, we will control the mesh in some area that we think that is really important. So we go to mesh and then apply mesh control. You have to choose the area or the edge. So we choose this. We will try to control the mesh on that ring because we think this is quite important when we apply the load. And on that part might get some reaction force or anything, or the stress and strain over there. Okay, and for the value, just change the mesh parameter, the size to the ratio is just the same. Okay. And for the global mesh, just mesh and create mesh. Curvature base again. Okay, just use the default of the software. Okay, not dark quality, just high quality. So for high quality, you remember that we go to the options, we already set that. Let's go on this first. Simulation. Simulations, options. And mesh, this high, we already say high. Okay. And you look at the mesh. In the control area, that's check again, simulations option, and on the mesh, we already ticked on the no penetrations, advanced options already there. And we have to go to the static study and check the property, and don't forget to check the improved accuracy for no penetration. Okay, and then run. That's it. Stress. Displacement. The maximum displacement is about 0.4. And strength. Okay. For displacement, double click to let the screen show, and if you use the deform shape, automatic deform shape, you get it like this. You see the ring go ellipse. Okay. That's deform shape. That more than usual. And if you don't like this, just go to the true scale. Okay, that would just not too much deformation. Okay, and also you can say animations. That is too fast. Just move the frame rate lower, like this. That will show you the deformations animations. And actually you can save as a file, AVI file, yeah, to show on when you do some projects to presentations. Okay, for the quiz that you have to submit it, so I would like you to try to do a different study, at least 2 more, to see how you change the image, how you get the converged result. I just supposed to see the displacement and the stress. Just 3 figures of the stress, 3 figures of the displacement, and show how it's converged. Depends on your remeshing. It's up to you how you go and define the mesh. Okay. And submit it in 1 page only. Maybe A4 page capture, or you can do it on the computer and cap it as a PDF file or an image file. Submit it on e-learning. Okay, you have about half an hour to perform that. And I also have a homework for you. That is just theoretical homework, just some explanation. So you can just do it and submit it within, I think I say Sunday. I set on e-learning on Sunday, 9th of October. And for quiz is today, the post test is today, midday, before midday.